My name is Joel and I'm back with another video on VPNs. Today I'll be looking at a specific concept called as the GRE tunnels, and then we'll also look at GRE over IPVSec, right? Both in the tunnel mode and the transport mode, right? So if you've seen my earlier videos, you would have come across the LAN to LAN, basic VPN configuration, basic IPSec VPN configuration, right? So what we did over there was more of a policy based VPN because we had defined ACLs which matched the traffic, right? For example, in this case, we defined ACLs which would go from 10.1 network to 10.3, and only when the traffic matched this particular source and destination, only then the phase 1 and phase 2 used to come up, and the VPN used to, and the IPsec and all of that used to take place, right? But this is imagine a production network where you have these networks getting added, the sites getting new networks added every day in and day out. Then it becomes really manually intensive for engineers, or it becomes really mundane to go on to every time to go on to the routers and update the ACLs, right? Because without defining the policies or without defining the ACLs to match the traffic, the VPN tunnels will not come up. So to solve this, we will look at GRE, right? GRE is basically the default mode of a tunnel, and in simple terms, GRE basically helps in creating a logical connection between two routers. Now in this case, let's say I create a tunnel between R1 and R3, then it appears as if it is like a virtual direct it appears as if these two routers, or R1 and R3, are directly connected, right? They are not, obviously physically they are not, but the configuration makes it seem that they are directly connected, right? So yeah, let's dwell into the configuration, and while we are configuring, we'll get to understand more about more about GRE, right? Let's start up the nodes. Okay, so let's open up the consoles for all the three routers. Wonderful. So yeah, let me clear this. Okay, I think that's good. Similar here as well, just so that we have a better visibility on the commands where I'm typing, right? Great. So what we do here is first let's set up the router R2. R2 is basically acting like an ISP for me over here. So let's go to the configuration mode. Let's do the configuration on the interfaces to start with, right? Let's put a couple of IP addresses over here, which would be maybe, let's say, 192, right? 192 dot let's go with 1 dot 10 dot, probably let's say 10.2, right? That should work. 255.0, let's do a no shot. Similarly, let's do the other side, that is 2/1, right? And let's put an IP address over here as well. And what do we do here? 192 1 dot let's say 20 dot, what do we do here? 20.2, right? 20.2 should be good. Okay, 255 5.0, no shot. That's it. So we are done with the R2 side. Let's do it on the R1 side now, right? So on the R1 side, let's configure the serial interface, which is 2/0, right? And the IP address is going to be 192.10.1 probably, right? 255. Then let's configure a couple of our loopback interfaces, right? And the IP address would be, let's say, 10.1.1.1. Great. So let's also configure the other one, loopback 1, right? IP address 10 dot sorry, not 10, it's 172 network 172.16.1.1, right? And that's good. Let's also configure default gateway, right, route, which would be 0.0.0. One more, and we'll put 192.1 dot probably 10.2, right? R2 is going to be my default gateway, so that should be good, right? Let's quickly check. Do show IP interface brief, right? So we have 2/0 and both of them are set up, which looks good. Let's do the same thing on the R3 side, which is going to be yeah, so let's do an interface. So 2/0, IP address is going to be 192.1.20.3 255 255 255.0 and where no shot, right? And what do we do? Yeah, so what do we do next? So we have done so we have configured the serial interface. Let's also put a couple of loopback interfaces, right? So let's put 10 dot maybe 3.3.3 255. Wonderful. Let's also put the other one, which is loopback 1. IP address is probably going to be 172.16 dot let's go with probably 3.3. all right, 3.3, yeah, that's good. 255 255 255.0 and no shut. Maybe we will also have to put the default route, right, like we did earlier, and we are going to use 192.1 dot probably let's use 20.2, should be good, right? So we have done all of that. Do show IP interface brief should give me the command output. Okay, so that's good. If I ping, let's do a ping to my R1, right? Do ping 192.1.10.1. Yeah, there you go. So there is connectivity between R1, the serial interfaces for R1 and R3, right? Now, the most important part, we are going to configure GRE, right? So to configure GRE, what do we do? So we have to define tunnel, right? So we are going to define a tunnel which on both my routers R1 and R3, right? When you define a tunnel, you need to define the tunnel source and tunnel destination. So these will be the public IPs. So in our case, it will be 192.1.10.1 and the destination over here would be 192.1.20.3, right, for this tunnel. And then you define it on R3 as well by reversing the IP addresses, right? And once we define a tunnel, we are going to define a private network for the tunnel as well. So in this case, we are going to define 192.168.1.0 network as the private network for the tunnel, right? So this is how the configuration looks. So let's do that configuration on R1. Fine. So let's go to R1 and let's do this. Yeah, so I have the tunnel and then the IP address for the tunnel, which is a private address 192.168.1.1. Then the tunnel source, which is 192.1.10.1, and the destination is going to be the R3 router, which is 20.3, right? So let's do that. Yep. So I've put my tunnel configuration on R1, and we'll have to do the same thing on R3 as well, right? So let me go to the R3 router. Okay, so the only difference here would be the IP address is going to be obviously 1.3, right? And mind you, this is the private network which is defined for the tunnel, right? And then you have the tunnel source, which in this case will be 20.3, and the destination would be the R1 router, right? So let's do that. Wonderful, right? So we have done the tunnel configuration, right? Let me probably go back to R1 and maybe clear the screen because it's all cluttered, right? So if I show you how the interface show interface tunnel, probably 1, yeah, there you go. So the tunnel is up and this is the output of that. You can see the tunnel has a source of 10.1 and the destination being 20.3, right? And yeah, that's pretty much the tunnel which we have set up, right? Now still I mean I'll be able to obviously ping the other side just like earlier. So let's say if I want to ping one, okay, I would obviously not be able to ping the 10.3 network, right? Let's try. If there is a confusion, let's try. See, it's not reachable, right? 10.3.3 is not reachable because this is a network which is behind the router R3, right? And unless we put a routing protocol, you'll not be able to ping this address, right? So though you have a tunnel over here, right, this particular address or the networks basically which are behind the routers are, you know, are not advertised, right? And as a result, R1 has no idea about this network, right? Similarly, it's the case where R3 doesn't have any idea about this, right? So now how do we do it? So we need to introduce a routing protocol, right? So let's put a very simple EIGRP protocol, let's say, right? Let's do it on R1 to start with. So let's do that here, right? So this is my EIGRP protocol on R1, router EIGRP, no auto summary. Then I'm advertising my networks. On R1 I have 3 networks. One is my 192.168.1.0, which is my tunnel network, private IP address space of my tunnel. This is my 10 dot network, which is behind the router, and then I also have a 172 network, right? So once we do that, we are going to do the same on the other side as well, which is R3. It's going to be the same here because the IP address space which I've used is pretty much the same. So yeah, we are going to do that over here as well. There you go, right? So awesome. So what did I do right now, right? So I introduced a routing protocol, EIGRP, and I have also set up a tunnel between R1 and R3. Remember, I earlier told you setting up a tunnel basically makes it look like 2 routers are directly connected, right? So if you look for a second over here, using the routing protocols, we have now successfully advertised the networks which were behind the routers, into the network, and we have also set up a tunnel between R1 and R3, right? So now ideally everything is connected, which means I can go to R1 and ping the network which is behind R3 as well, right? So I must have here, see, let me try this now. If I ping, I'm on R1, and if I ping the network which is behind R3, which is 3.3, should work. Yeah, there you go, it is working, right? Which is great, right? So we actually set up GRE, right? Now to understand a very interesting concept, what we are going to do is we are going to do a little bit of packet capture. Okay, so yeah, GNS3, I think it does come with Wireshark. So let me try to do that. Let me see if I can. Yeah, so there is something called as packet capture. Let me try this. I think this should, yeah, there you go. The Wireshark opens up, right? So as you see here, you can see the EIGRP packets, because of my EIGRP protocol, the hello packets, basically the heartbeat packets, are basically being shared, right? And these packets are actually moving on the tunnel, right? So if you see, let me like probably pick up a particular packet and let's see how it looks. So this is basically GRE encapsulation. So every single packet now, if it is destined to the other side of the network, in this case the 192.168.1.3, right? So if you look at that particular network is on R3, right? So we have this particular yeah. So if you look at this particular packet capture, you can see that you have a inside header, then you have GRE, and then you have a outside header, right? The outside header will obviously be a public IP, whereas the inside header, right, is encapsulated, and the inside header basically consists of the private addresses, right? And GRE encapsulation makes it possible, right, for the data to be shared, for the data to be communicated across the tunnel, right? So so this is actually one packet which is going from R3 to R1. It is basically a EIGRP hello packet, right? And that's why it has a source address of 1.3 and a multicast address of 224.0.0.10, right? And whenever a router, so in this case the router R3 looks at this packet, right, 192.168, and it is destined to this particular network, what it does is it looks that it finds that the packet has to be sent over the tunnel, right? And so it will encapsulate with the tunnel source and tunnel destination, right? On R3 router, the tunnel source is 20.3 and the destination is 10.1. So it encapsulates this packet inside the tunnel, and the packet is sent, right? The R2 router, which is the ISP, obviously will not see the inner address. It basically operates only on the outer address, right? So with respect to R2, it just understands these two networks. It doesn't understand any networks which are behind the router or the private addresses, right? Yeah, so that's how actually GRE works, right? Every packet, let's say we're talking about R1 and R3 here. So every packet which has to be, or which moves along the tunnel, right, which has been set up between R1 and R3, right? So the router quickly checks the routing table. So in this case, let's say to show IP route, right? So if you look at the routing table, you can see here there is a directly connected route mentioned with respect to tunnel. So 192.168.1.0, and you have it to be the directly connected network to tunnel. So when the router sees that a packet has to be sent on this particular network, it sees that there is a tunnel associated with it, right? And when it sees that a tunnel is associated, it goes up and finds the tunnel source and destination and encapsulates the packet and sends it across, right? So that's how GRE works. Okay. Now we are going to go a step ahead, and let me continue having this capture up here, because I want to show you something as well. Just keep in mind that the packet here appears to have a length of 88 bytes, right? The hello packet seem to be 88 bytes. And also the other important thing which you need to notice here is that we have just used GRE, right? The packets are not encrypted, which means we get to know everything about the packet. We know that it's a EIGRP protocol packet, you know the version, you know that it is a hello packet, and all the information is very much clear text. So if an attacker sits somewhere in R2, he can actually snoop in on all the packets, just like what I'm doing here, and kind of like do a lot of inject routes and do a lot of bad things to the network, right? And now that's where, that's a disadvantage of just using GRE. So that's why we need to use GRE with, IPSec. So IPSec provides that encryption which is needed, right? So what we are going to do now is something called as GRE over IPSec, right? So IPSec basically carries, GRE, and it encapsulates, right? So to do that, you would have seen my earlier video. We did a very nice configuration for IPSec. There were 4 steps specifically, right? And we are going to repeat them over here with some slight modification. Again, I'll take you through them. So let's start with that, right? So let's do the IPSec configuration between R1 and R3. Okay, let me clear this quickly, which is good. Let me also clear the other side. Wonderful. So let's continue. So what we have done now, we have set up a tunnel between R1 and R3, but we found out that all the data which is which is going along is like in clear text. So we want to use IPSec to encrypt it, right? So let's start. So on R1 we are going to do this, right? Let's start doing IPSec. So we have the phase 1 configuration for IPSec we did in the previous video, right? We have the ISACAM policy, and then you have the authentication 3DS and hash, and the Diffie-Hellman group mentioned, right? And we also have the ISACAM keys, right? So which is good. Let me put this. So this is my phase 1. So what is my phase 2 configuration, right? The phase 2 configuration looks like this, right? As simple as that. It basically is a transform set command. ABC, it could be any name, it's just a name, and we define the 3DS and SHA HMAC over here, and obviously the keys are not needed because phase 1 is something which establishes and exchanges the Diffie-Hellman keys, which are in turn used for phase 2, right? We saw that in the earlier lab session. So okay, we have done the configuration for phase 2 as well. Now in the earlier video we used something called as crypto maps, right? Crypto maps was something which is binding my phase 1 phase 2 together, right? So here we actually don't need crypto maps, because what we are doing here is we are using a tunnel, right? And we don't explicitly have to put a ACL like we did earlier, right? Earlier we defined an ACL to identify the interesting traffic, but here, since we want to encrypt all the data which is going on the tunnel, we don't have to explicitly define a ACL, right? And we don't even have to define a tunnel a peer as well, right? So yeah, so we are not going to use cryptomap here. We are going to use something called as a IPSec profile, right? So the IPSec profile looks like this. So this is like the last part of the configuration here, right? So this is what we do. So we create an IPSec profile, right? And we are going to attach the transform set, or basically the phase 2 tunnel which we created now with the IPSec profile, and then we are going to define our tunnel, right, which we have created earlier, the GRE tunnel, and I'm going to attach my IPSec right, and I'm going to attach my IPSec profile to the tunnel, right? So there you go. So that's only the configuration which you wanted to set up GRE over IPSec. So that's what I've done on R1. Now I gotta repeat the same thing on R3 as well. Okay, so let's do that. So on R3, let me pull the configuration up. Yeah, there you go. So we have phase 1, we have phase 2, and sorry, so much is phase 1, this is phase 2, and we are going to do the IPSec profile and the tunnel, and we are applying the tunnel, right? We are applying the profile to the tunnel. Okay, just to remind, we are not using crypto map here because we don't have an ACL to match the traffic, right? We want all the traffic which is going on the tunnel to be encrypted. So we don't actually have to use crypto map. You can use a profile, and we attach our phase 2 tunnel to that, and then use a tunnel and attach the profile to it. right? There you go. So that's the configuration which goes on R3, right? What have we done here? Is it looking good? It should be. So how do we check this? Have we actually set up GRE over IPSec? Couple of quick commands to check. Do show crypto, maybe ISACamp. Let's check the phase one if that is working, right? There you go. So both the tunnels are up. Like in the previous session, we don't have to ping the router R1 to actually set up the phase 1 tunnel, because we have set up EIGRP and ERGRP hello packets are continuously moving in the network, and since we have defined the tunnel, anytime anything moves on the tunnel, we basically have the phase 1 session and the phase 2 sessions coming up, and the VPN is up. So that's why even without me pinging R1, we see that phase 1 tunnels are up, right? Because we have the continuous churn of the EIGRP hello packets, right? Let's also see how the other phase 2 looks, right? So do show crypto IPSec SA. So this is my phase 2. You can see that there are a lot of packets already being encapsulated and encrypted, again because of the EIGRP packets, right? And this is my phase 2. The phase 2 has been set up. Both the outbound and inbound is working. Now let's quickly jump down to my Wireshark, right? As you see here, the hello packets have now become you can clearly note from the pattern that the packets which are repeating the most have a size of 140, right? And these obviously are the hello packets. So observe that the hello packets, the length has increased from 88 to 140 here, right? And the reason being because we have IPSec encapsulating GRE, right? So because of that, so I have picked up a packet here, and also note that we don't have any data. Everything is encrypted over here, right? So we really don't know if this is a EIGRP hello packet or it's an update packet. I mean, no information. You just the packet just tells that it's a ESP. So ESP is the protocol, right, for phase 2, and phase 2 in IPSec, right? And ESP protocol basically is encapsulating everything inside, and as a result of that, we have encrypted the traffic, right? So, but obviously the size has increased. The size has increased from 88 to 140, which means if you do a diff between 140 and 88, you get to know that 52 bytes is basically the IPSec data, right? So that's something which I wanted to show here, right? Now what we are going to do is, if you look carefully at this particular packet, okay, we will not be able to see here. Maybe let's see if I can show you that. Okay, probably not. Okay, maybe not. Okay, so yeah, okay, I think we can see. We can still see here. Give me a minute. I think yeah, that works. So if you look a packet over here, you get to know that there is encapsulation happening. Yes, right? So you at the innermost side you have you have your payload, right, which is getting encapsulated, and that is again right, so that is again encapsulated by the GRE packet, right? And the GRE packet has the headers, right? I told you earlier that whenever a packet enters the tunnel, the router encapsulates the tunnel source and tunnel destination. So in this case, this is the tunnel source and this is the tunnel destination. So we have the router encapsulating the payload with the tunnel source and destination, and then my IPSec protocol, the ESP, also encapsulates or again adds the header, right, which is again the same header. You can see here the source and destination over here is very much same as source and destination over here. So you can see that there is a clear duplication happening here, right? And obviously you don't want to send more bytes on a medium. You always want to shrink it. Now that is where a new mode of IPsec comes into picture, and that's called transport mode, right? By default, the tunnel mode is used, and in tunnel mode, you will have duplication happening, duplication of the headers in this way. But if you use the transport mode, we can actually remove this duplication, right? Because it's a simple waste of data. You really don't want two duplications. So when you use transport mode, right, these this part of the information will be removed from the packet, and as a result your packet shrinks. It will not be 140 bytes, it will be less than that. So we could see that, right? So let's do that. So to let me also show you that how you can find as to what you're running is a tunnel mode or a transport mode. So if you see the output of this command, which is do show crypto IPsec SA, you can see that there is a tunnel mentioned here. Yeah, over here, right? So you can see that there is something as a tunnel mentioned. Now I'm going to change this configuration on R1 and R3, and then we will see that that changes, right? So let's do that. So before doing that, let me probably clear the um, crypto configuration on both the sides, right? And let's do this, right? So let's pull this up, and yeah, so this is my phase 2 configuration. I need to just enter that, and I need to mention mode to be transport, right? There you go. So I need to do the same thing on the other side as well. Okay, so we have done that. Let's just see if that worked. Do show crypto, right? IPsec SA. Okay, it has still not come up. It still shows me as the tunnel mode, right? Let's give it a minute. Maybe let's do this again. To show crypto. Yeah, so you can see here now the the mode has changed. It has changed from tunnel to transport, right? I think it should have worked here as well. Now it takes maybe a little bit of time. I was just rushing. To show crypto IPsec SA. Yeah, there you go. So it has changed. It has changed from tunnel mode to transport mode. Now let's go back and see our Wireshark. You can clearly see, the size of the packets has reduced from 140 to 124, right? You can see that, right? Yeah. So the size of the packets has reduced. The reason being the duplication has been removed, because like I said earlier, when you use GRE or IPsec, by default we have the innermost packet which is encapsulated by IPsec. The IPsec adds the IP address, which is um, basically the public IP address, right? When IPsec is encapsulating, it adds the address, and then because we have GRE, right? GRE also adds the same address. So it's basically duplication of the duplication of the IP addresses. So using transport mode, you can actually remove them, and then the packets strings, right? So we started with 88 bytes, which was only GRE, and then we moved to GRE over IPsec, which gave us 140 bytes, and then we finally used GRE over IPsec in transport mode, which gives us 124 byte, right? So that was everything which I wanted to show here. So we successfully set up GRE over IPSec in tunnel mode, which is the default mode, and then at the last we also set up GRE over IPSec in transport mode. Right? Thank you.